All right, so area under the curve. Here we're going to look at some concrete examples, and I'm going to introduce a probability distribution that we're going to be using for examples throughout this unit. So similar to the arrest data last unit, you're probably going to be really, really tired of it within a couple weeks. And specifically, this is going to be a probability distribution that describes the number of thefts that's likely to occur at a big box store in a given month. So we're going to say the number of thefts is our outcome. We're going to be looking at the probability of number of thefts occurring. We'll say over the course of a month, what's the probability that a certain number of thefts is going to happen in this store? The mean of this probability distribution, or mu, is 65. So in other words, the most likely number of thefts that we would expect to occur would be 65 thefts. It's less likely that you're going to have a lot more thefts than that. It's less likely that you're going to have a lot fewer thefts than that. And so this would be one of those variables that isn't continuous, but it's close enough for our purposes, in the sense that we have a lot of different values that you might find along this x-axis here. This distribution also has a standard deviation, which we'll say is 15. And so like you saw on the slide, this just tells you how fat or how skinny our distribution would be. And this isn't necessarily to scale, and with any of these, I'm not really going to be drawing them to scale. But you should know that this is a standard deviation of 15. So let's start talking about area under the curve. The first thing to note is that in this probability distribution, as in any probability distribution, the area under the curve is going to equal 1. So all of this area that I'm shading here is going to equal 1. And that's because there is a 100% probability that some number of thefts is going to occur in this store, including 0. That's a possible value as well. And as a quick note, we're going to use normal distributions to model variables like this. But in reality, what we have is probably a probability distribution that looks more like this. Where this is 0, because you can't have fewer than 0 thefts. That would be somebody, bringing things into your store and putting them there to sell. And then this would be some point at which it just becomes really, really, really unlikely to the point of it being negligible or almost 0 that you're going to have more than that. So technically, you can imagine there sort of being a long tail that comes off of here, but we're going to say this is negligible to the point of being indistinguishable from 0. So we're just going to ignore that, and we're going to treat this like it's a true bell curve and not skewed. And so using a normal distribution like this is going to be appropriate for any variable where you can essentially say that the probabilities that matter make up a bell curve. So thinking about height as well, technically it's possible for a person to be 9.5 feet tall, but at some point we're going to say that height is negligible, and so that would just be not really worth including in our bell curve. So as long as a bell curve, more or less reasonably describes the values that are likely to occur, it's appropriate. So even though it would be possible that somebody would steal like 1,000 things and you'd have some amount of probability of that happening way out here, we're not going to be considering it in this example. All right, so back to this idea here. Given that this bell curve, more or less tells us the probability of different numbers of items being stolen, and it's more or less symmetrical, we're going to say that the area under this curve equals 1. Anything past the curve is negligible and so small it's not going to be counted. And what this area of 1 tells us is that there is a 100% probability of some number of items being stolen. That's being. All right, so area under the curve, first things first, all of it equals 1, and that tells you there's a 100% probability of some items being stolen. Now I want to get to that next point, though, which is the idea that the area under the curve between some number of values, some set of values, tells you the probability of getting outcomes between those values. And specifically, I want to think about what happens if we shade the area here between 0 and 65. So now half of the area is shaded. Half of 1 is 0.5, so we'll be able to say that this is an area of 0.5, or 50% of the total area is shaded. What this means, since we have an area of 0.5, it means that we also have a probability of 0.5. And what we said before is that the area between two values is equal to the probability of something occurring. So if we have an area of 0.5 between 0 and 65, because this thing is symmetrical, that means we also have a probability of 0.5. And this probability corresponds to the probability that between 0 and 65 items will be stolen. So we could say that there is a 50% chance that between 0 and 65 items will be stolen in a month. So this is the basic idea behind area under the curve, where the area under your curve corresponds to probability, and the area between two values corresponds to the probability of getting an outcome between those values. So we know that 50% of our distribution is between 0 and 65 here, and so we'd have a 50% chance that 65 or fewer items are going to be stolen from this store. Now, you'll remember on the slide I also talked about something called the empirical rule. And what the empirical rule does is tell you the probabilities that you're going to get outcomes between 1, 2, and 3 standard deviations from the mean. So I'm going to draw out what that looks like here. We have our normal distribution with a mean of 65 and a standard deviation of 15. So if you go out one standard deviation, we're going to be adding 15, we're hopping 15 over, and we're at 80 items. We go out one standard deviation on this side, we're subtracting 15, and we're at 50 items. So here 80 is 65 plus 15, and 50 is 65 minus 15. So we'd say that between 50 and 80 is within one standard deviation of the mean. So we've got one standard deviation on either side. And we can come up with values for 2 and 3 standard deviations as well. So if we go out another 15, we're adding 15 to 80, and we're at 95, which again is equal to 80 plus 15. So we've just hopped out another 15 units here, or in other words, another standard deviation. And we can do that on this side as well. So what I'm doing here is I'm dividing this chart into sort of jumps in both directions of different standard deviations. We do another standard deviation jump this way, so that's 15 units in the negative direction. We're subtracting 15 from 50, and we're going to get 35. So 35 is, of course, 50 minus 15. And again, what I'm doing now is I'm just marking this graph off in these standard deviation intervals, and then I'm going to show you what we're going to do with that after I'm done with this. I'm going to do one more, which is going to be one more standard deviation jump in this direction, which brings us to 110, which is based on 95 plus 15. And then we'll do one more in this direction, which brings us to 20, which is going to be 35 minus 15. So we have this normal distribution, and we are breaking it up into intervals, and each of them is the size of one standard deviation. So here at 80, we're at one standard deviation in a positive direction. We go to 95, we're now at 2 standard deviations in a positive direction, so we're jumping 1, 2. And at 110, we're at 3 standard deviations in a positive direction. So we've jumped 1, 2, 3 intervals of 15 to get to 110. We're doing the same thing going in a negative direction. So from 65, we move -1 standard deviations to the left to get to 50. We're at -2 standard deviations to the left to get to 35, so that's a 1, 2. And then we're at -3 standard deviations to the left, standard deviations when we're jumping 1, 2, and then 3 jumps of 15 to get to 20. Why is this important? Well, the reason is that we have something called the empirical rule. And the empirical rule tells you the probability of getting values within 1, 2, and 3 standard deviations of the mean. So in other words, it's going to tell us the area that falls within 1 standard deviation of the mean, 2 standard deviations of the mean, and then finally 3 standard deviations of the mean as well. And what that's going to let us do is find the probability of getting between these different numbers of values. So I'm going to write out the empirical rule that I'm going to draw a new one of these for each set of standard deviations and write out what the probability is more specifically. So the first thing that the empirical rule tells us is that within 1 standard deviation of the mean, so between -1 standard deviation and +1 standard deviation, you're going to find 68.3% of your area. Or in other words, a probability of 68.3% of getting between plus and -1 standard deviation of the mean. Within 2 standard deviations of the mean, so between -2 and 2 standard deviations, we're always going to find 95.5% of our area. And finally, within plus or minus 3 standard deviations of the mean, so that's from -3 to +3 standard deviations, we're always going to have 99.7% of our total area. And the key thing here, and what's really cool about the empirical rule, is that this is going to be true of any normal distribution that you have. So as long as it's a normal distribution, so as long as it has this specific bell shape, doesn't matter what your mean is, it doesn't matter what your standard deviation is, it's always going to have these qualities where 68.3% of your outcomes are going to be within plus and minus 1 standard deviation of your mean. So there'll always be a 68.3% chance that you're going to get an outcome between -1 and +1 standard deviations. There's always going to be a 95.5% chance that you're going to get an outcome that's between -2 and 2 standard deviations. And there's always going to be a 99.7% chance that you're going to get an outcome that is between -3 and 3 standard deviations. So let's look at what this tells us specifically about numbers of thefts. And I'm going to start with 1 standard deviation on either side of the mean. So we have a mean of 65, and here we're just going to go out 1 standard deviation on either side. So as we showed in this chart here, if you go out 1 standard deviation on either side, you're jumping 15 this way, and that brings you to 80, and you're jumping 15 this way, and that brings you to 50. So plus and minus 1 standard deviation brings you to 50 and 80. The empirical rule tells us that the area between plus and minus 1 standard deviation of the mean is always going to be 68.3% of your total area. or since we have a total area of 1, an area of 0.683. This means that our probability is going to be equal to 68.3%. So we've got 68.3% of our area, also known as an area of 0.683, and a probability of 68.3%. This probability, based on how probability distributions work, is equal to the probability of getting an outcome that's between -1 standard deviation and +1 standard deviation. In other words, a probability of between 50 and 80 items being stolen. So this part 1 of the empirical rule tells us that there's a probability of 68.3% that between 50 and 80 items will be stolen. So that's the first part of our empirical rule. And we could also redraw this with just the mean and standard deviation marked off. So in other words, we've got our mean here, we've got our mean +1 standard deviation, and we've got our mean -1 standard deviation. And we're looking at the area between those two things. And it's always going to be equal to 68.3%. All right, our second part of the empirical rule tells us what we can find within 2 standard deviations of the mean. So we've got our mean here, it's 65. We know that if we make 2 jumps of 15 away from the mean, we get to 95 going out here. So this is a jump of 15 and another jump of 15. So this goes to 80 and this goes to 95. And then if we do 2 jumps of 15 in the negative direction, we're going to end up at 35. So this is +15 and +15. This is -15 and -15. And I'll add these in here as well. So the second part of our empirical rule tells us the area under the curve within 2 standard deviations of the mean. And specifically, the area under the curve is going to be 95.5% of your total area, or an area of 0.955. This means that your probability is going to be equal to 95.5%. So in other words, there's a probability of 95.5% that you're going to have an outcome that is within 2 standard deviations of the mean, or more specifically, between 35 and 95 thefts. So based on the empirical rule, we could say that there is a 95.5% probability that between 35 and 95 items will be stolen. So anytime you see a problem or an example that's using a probability that is part of the empirical rule, you want to think about these charts here, and you want to think in terms of standard deviations away from the mean. With this one, I'll also redraw it here in the same way, where you can think of this as being the mean here, and then we've got the mean +2 standard deviations and the mean -2 standard deviations, and we're looking at the probability between them. So this is the empirical rule applied to a probability distribution that has values here, and then this is one where it's just labeled in terms of the mean and standard deviation, but it's showing the same thing. All right, and last but not least here, I'll go through the example for 3 standard deviations on either side of the mean. Here we have our overall mean here, which is 65, and now we're jumping out 3 standard deviations, both to the right and left. So +15, +15, and +15. That brings us to 110 items, or +3 standard deviations. And then going out 3 standard deviations to the left here, this brings us to -3 standard deviations, or a value of 20 items. And using the empirical rule, we can find the probability of getting an outcome that's between 20 and 110 items, or in other words, an outcome that's within 3 standard deviations of the mean on either side. And the empirical rule tells us that the area is going to be 99.7% of the total area, or 0.997, since again it's out of 1. And it corresponds to a probability of 99.7%. So just like in the other ones, we're going to use that probability to say the probability of getting a value between these two numbers. So we'd say that there is a 99.7% probability that between 20 and 110 items will be stolen. And my advice to you here, when you do these problems on the problem set, is if you're unsure of something, just draw out the graph. Usually, I think putting things where they go on the normal distribution is really, really helpful in thinking through these sorts of problems. And last but not least on this page here, I'll just draw this one without the actual numbers in here. So what we have is the mean, and then we have the mean plus 3 standard deviations and the mean minus 3 standard deviations. And we're looking at the area between those values there, right, 3 standard deviations. Okay, so that is one application of a normal distribution here. And it's a way of finding the probabilities within certain numbers of standard deviations from the mean. But this might raise the question, how would you find the probability of getting outcomes between two values that are not within exactly 1, 2, or 3 standard deviations of the mean? So for example, could you find out the probability that more than 100 items will be stolen? Or that between 45 and 70 items will be stolen? The answer is yes, but in order to do that, we're going to have to go back into the PowerPoint and learn some new concepts.